Hi, I'm Leif, and in this video we're going to show you how to look inside the CWL metrics so that you can sort of debug them and sort of understand the different continuation functions, weighting functions, and log likelihood functions that are being generated. And so we have a notebook at the bit.ly address here that you can click on or visit, and then check out the examples there. So this is what we have in our notebook. So obviously we need to pip install cool.val, so we have all the machinery. And then you can see that I'm importing a whole series of different metrics and some other bits and pieces so I can plot the CWL functions. And then we also need our ranking object so that we can construct a topic and then pass it to our metric to run. I've just defined a few functions here just to make some nice plots for the course of the video, but let's just scroll down and look at how we can build a query or a topic to then evaluate. So here we've got about 15 items, and here we're assuming that we have 15 items that are all the same cost. And we'll make another one where we have variable costs, the number of seconds it takes to process the different items. And we'll build a couple of different queries. So here we assume that all the items are relevant and give us one point of gain for each item. And then we'll make a query 1, which has unit costs. So for the ranking, we give it a name. We'll say it's query 1. We'll pass in our gain vector, and then we'll pass in our cost vector, and then the ranking will be constructed. So we have that in query 1. And then we'll do the same with query 4, but this will be with variable costs. Then we'll have another couple of queries which have relevant and not relevant items in between. And then we'll change the gain here in these other two queries, right? So we have ones of 0.6 and 1 and 0.4 and 0 and 0.2. So now we have variable gains. So now we've sort of taken these rankings, combined them together. So now we have 6 different queries, right? So the last 4 have the variable costs, and the first 3 have the unit costs. And then we know that the 1 and 4 are the all relevant. 1 and 2 and 5 are the some relevant, and 3 and 6 are the some are relevant, but they've got different gain values. So now we've got what we want to evaluate encoded. Now we can define some metrics that we've imported. So we've just set up precision metrics. So here P at 5, AP, discounted cumulative gain with at 5, reciprocal rank bias precision with a theta of 0.6, inst with a target of equal to 2, so that's the desired amount. The information foraging theory metric, it has a lot of parameters, and the U measure here as well. And so now we have created our metrics. We can start to use them, right? So here I'm just going to set the P precision 5 metric P and ask the framework to measure the query 6, right? So that's the ranking with the costs and gains there, right? And so once we call the measure, it will return the expected utility, but it will also just store all the values within the object, right? And so we can then ask the object for the metric's name, the expected utility, the expected total utility, and so forth. But we can also ask it to give us the W vector, the C vector, and the L vector. I suppose I should have put those in the other order to make them cool. And you'll notice here I have to pass through the query again in order to get those vectors, while for something like P at K, that C vector and W vector and L vector are always the same. For different queries and different orderings for other metrics, these, because if we use an adaptive metric like inst, then the C, W, and L is dependent upon the input, right, or the ranking. we can also just get the list of scores. And so when we run that, then we're getting out all the different values that we see in, say, cool-eval. And you can see down here, crucially, the different vectors coming out. So here the continuation function is 1, 1, 1, 1. And then the fifth one is 0 because it stops. And the weighting vector is 0.2 for the first 5, as we'd expect. And the last likelihood says here that it stops at the fifth one, right? Because it always does. Okay, so that's the way we can access the different metrics. But and so we can take those, and here I've just written a little function to spit out for a given set of queries to make the measurement and then report out, which is just a function of the metrics, to report out the different values. So when I call this, so passing in the precision metric for a particular queries, you can see here I have my results come out, and that the expected depth is always the same because it's always P at 5. For our first 3 where we used unit costs, it's always going to be 5, and the expected cost is always going to be 1. But when I did pass in the costs on the second, on the 4, 5, and 6, you can see that the expected total cost is now 16, and the average cost is about 3.2 seconds per item to look at. Of course, the expected utility and expected total utilities don't change for a given topic, so it's still 1 and 5 and 1 and 5, or 0.4 and 2, right? But we can see that there's different costs being generated now, right? And so here we can see that obviously for the first query there we're getting a lot better performance, where the expected utility is 1 per item, and we get a total of 5. Well, that's what the expectation is, right? Of 5 units of relevance if we were to go to P at 5. And of course, we can do the same with, like, average precision, pass that through. And now we start to see that with average precision, because the way that the function works is that if it sees a non-relevant item, it continues. But if it doesn't see if it sees a relevant item, there is some probability that it doesn't continue, or there's lower probability of it continuing. Then we see that the expected depths and the expected total costs vary between the topics. It's not always consistent, right? And we also see that we get different values of the expected utility here and the total expected utility. And so again, we can work out the sort of rate of gain. So that would be the expected total utility divided by the expected total cost, right? And so that would give us gain per second, for instance, in this case. For RBP, we see that the expected depth is always the same. It's 2.5 because our theta is always the same. So it's a static measure in that respect. Obviously, the costs change slightly, and the expected cost per units also change accordingly, right? And then similarly, we can do the same with INST, and the same with information foraging measures and the U measure and so forth. Right, so that's one way we can inspect them, inspect the values within them. And this is essentially what cool-eval is actually reporting to us, right? But we want to see inside the metrics. So what is happening, or what is going on? So, given that we can pull out the C vector and the W vector and the L vector, like I showed you before, well, we can plot them. So rather than just plotting out the vectors or printing the vectors, we can we can actually do the plots. So here I'm just passing through the queries, and it's going to plot the C function for all the queries. Now, because it's P at 5, it's always the same C function regardless of the query, regardless of whether you see all relevant or all non-relevant, it will still look the same. And so here you can see it's continuation till we get to the 5th element, and then it stops. And the weighting function is 1/5 for the first 5, and the last likelihood stops at 1. So pretty straightforward there, so that makes sense. When we do it for RBP, again, that's another static measure, right? So we set the C at 0.6, and then you can see it's 0.6 all the way across here. And then the effect of that means that you see that you get an exponentially diminishing weighting function accordingly. And interestingly, the likelihood of stopping at a particular point also follows the same shape and is actually the same values as well. Moving on to something like discounted cumulative gain, we find that the C functions actually look quite different, right? And so here you can see that it's still a static measure because we only have one being shown, but the probability of continuing increases as we go deeper until we get to our fifth element, because that's our hard cutoff, and then we stop. And so this means the weighting function is kind of a little bit wonky before it turns into all zeros. And the likelihood function, or where we're likely to stop, well, we're equally likely to stop at the first one as we are at the last one, and there's less likelihood of stopping somewhere in between, which is kind of a little bit weird, I'd say. For inst, now we can see, because this is an adaptive measure, we can see that we have different values depending on the query. So it's based around the amount of gain you're receiving. So we only see three curves here, and you can see that when it's always relevant, then we get this red line here, and when we're getting the gain throughout the process, the probability of continuing actually increases through the course of the interaction, which is kind of interesting. But we see there's a sort of monotonically decreasing weights and likelihoods for the inst function, right? And of course, if we change the inst measure, like change it from 2 to 3 or 4, then these curves will change correspondingly. For information, the information foraging metric, right, it's much more complicated. And so now you can see that this is just for the last three. Then we get quite different shapes. This one's even going up and then down, because as the user experiences different amounts of gain, like encounters items that are gainful or not, then that will change their probability of continuing, right? And so initially, if they don't get anything good, which is like in topics 4 and 5 and 6, then there's a lower chance they'll continue. But if they do, the second item is useful, it has some gain, then it gives them a little bit more of a spur on, like, so their rate of gain is increased now to continue on with subsequent results. Of course, if they get enough gain, then they're much more likely to stop during this process. So if they get another relevant item, we set the T to 2, just like in inst, so they're much more likely to stop rather than continue, because their stomach's full. And then so you can see the corresponding weights. So you can see that this measure is very much more sensitive, but also giving very different sort of curves, right? And it's more sensitive because it's making different predictions on where people will stop based on their experience, right? That they're encountering. And you can also look into the U measure, right? And you obviously can do this for all the different ones, and you can start to play around and start to debug your metrics, see if they make sense, see if they're acting accordingly, right? And following our different intuitions. So here, when they're all relevant, that's all things that are, actually when they're all uniform cost, it's all fine and dandy, and the probability of continuing just goes down. But when the cost in the U measure change, then the probability of you continuing changes depending on whether you've seen consumed a very long item or a very short item. So shorter items mean that you're more likely to continue because it's you can read through them very quickly, but a longer item takes a lot longer, so you may not necessarily continue past it, right? And so that's the intuition behind the metric, and we can kind of see that's reflected here, right? Which is pretty cool. Okay, so that sums up how to look inside the CW metrics using the notebooks. Thank you for listening, and remember to like, comment, and subscribe.